Welcome to the Bible and Science. This is Dave Prentice. I'm a retired public high school teacher, certified in all branches of science and math. I've also taught on the Bible and Science for many years, both in the U.S. and on many overseas mission trips. This is episode 22 of the Bible and Science. We're dealing with the age of the earth, and this is part 2 of that topic. Why do people believe the earth is old? Number one, that's what they were told. Number two, they believe that it takes millions of years to form a fossil, and we saw in the last episode that it doesn't. It can happen very quickly. Number three, which we're going to work with today, is the idea about radiometric dating. They misunderstand and they think it proves something or other about the age of the earth. And then we'll also spend some time discussing geologic features later on. So if we want to know how old something is, we need a clock of some sort. And there are certain characteristics. We need to know the initial conditions. If I set my alarm for 6 a.m., I need to make sure that I had the correct time set on it when I went to bed. And then we also need to know the known rate of change. The clock doesn't always have to run at the same rate, but if it changes, I have to know when and by how much. So if I've got my alarm clock set to get me up in the morning, I need to know that it's going to be running at a steady rate. Then also, I need to know that the clock has not been reset or tampered with. Quite a number of these things that we'll talk about involve things that are water soluble. So if a rock has ever gotten wet, we really can't trust that it's been a closed system the whole time. So we should use as many different methods as possible to determine a maximum possible age of something. Less than 10% of the available dating methods point toward a maximum of billions of years. The rest point toward millions or even, in some cases, thousands of years, and this is a maximum possible age. It could be anything less. So let's get back to the idea about radioactive dating. An atom that has too many protons or too few protons as compared to the number of neutrons is not going to be stable. We don't understand why nuclei don't fly apart, but it's something to do with the ratio of neutrons to protons. So if it has too many neutrons or too few neutrons, it's probably going to be unstable, and it's going to try to release excess potential energy by sending out various types of particles or releasing some sort of radiation like gamma. So the types of particles that can come out, the most obvious one would be alpha decay. This is where the nucleus ejects 2 protons and 2 neutrons at the same time. That lowers the atomic number, which is the number of protons, by 2. And it lowers the mass number, which is protons plus neutrons. It lowers that by 4. The other type of radioactive decay, there may be unknown things, but the other type that we're very familiar with is called beta decay. In the nucleus, you have neutrons, and if one of them breaks apart, what used to be a neutron is now a proton and an electron, and the electron escaped from the nucleus. So what's there now, in the nucleus, you have the same number of particles, except that one of the neutrons is changed into a proton. So that increases the atomic number by 1, but it leaves the mass number unchanged. The mass is not exactly the same, but a neutron and a proton are so close in mass that the mass number stays the same. So the radioactive atom starts out as one element called the parent. It decays into a different element that's called the daughter, the radiogenic daughter, produced by radiation. The daughter may or may not be radioactive. Many cases they are, but some they are not. If it is radioactive, it will in turn become the parent element of another radiogenic daughter element. So how can we tell how fast this is going on? Well, there are some radioactive parent elements that decay into the final daughter product in one step. For instance, carbon 14 turns to nitrogen 14, but there are others that go through many intermediate steps. For instance, uranium 238 goes through 14 steps before it turns into lead 206. Why is this happening? We don't know. Why is it that one atom decayed while the one next to it did not? We don't know. So we can't predict which individual atoms will decay. So what we do is we take a large sample of them, trillions and trillions and trillions, and we average together a large number of atoms of that element to calculate the half-life. That's the amount of time it takes for half of a sample to turn into the daughter product. So after one half-life, half remains. After two half-lives, it's 1/4. After three half-lives, it's 1/8. After four half-lives, it's 1/16. Each half-life, you have half as many remaining as what you started with. So these are some of the commonly used radioactive decay, radioactive dating methods. The parent, carbon 14, will turn into nitrogen 14, and the half-life is calculated at 5,730 years. Potassium 40 will decay into argon 40, and it's estimated at 1.3 billion years. Have we been watching for 1.3 billion years? No, this is a calculated amount. Uranium 235 turns to lead 207 in 713 million years. Again, it's a calculated amount. We've only been watching this for just a little over a century. Uranium 238 turns to lead 206, and it's supposed to take about 4.5 billion years. Rubidium 87 turns to strontium 87 in about 47 billion years. Calculated, calculated, calculated. The half-lives of various things range from some that are in the microseconds to others that are supposedly in the billions of years. But radioactivity was only discovered around the late 1800s, early 1900s, so it's only been about a century and a quarter, so there's no way to verify long half-lives. We haven't been watching for billions of years, haven't even been watching for thousands or hundreds of years. So we have to calculate what the decay rate is. So if you want to know something using a clock mechanism, those characteristics are necessary. You have to know the initial conditions. You have to know that the rate of change, what the rate of change has been. It's okay if it changed as long as you know when and by how much. And you also have to know that the system hasn't been tampered with. It has to have been a closed system. So if you want to use some rocks, some mixed up rocks for accurate radiometric dating, here's what you need. Most rocks are going to contain a mixture of elements. Many include a radioactive one called the parent and a radiogenic daughter, and they may have several other steps in between. But if you want to be confident, you need to know what was the initial percentage of parent and daughter in the rock. Were you there? No. We have no way to know that. We assume usually that it's 100% of the parent and 0% of the daughter at the beginning. We have no way to know that. We don't know how the parent came into existence, so maybe it went through steps on the way. So the radioactive parents came from somewhere, but according to the evolutionary models for the origin of the elements, the daughter elements could have been present to use as building blocks in making the parents in the first place. If that's the case, there would automatically have been a mix of the daughter and the parent from the beginning of the time that this whole system started, which presumably would be the beginning of the Earth. We have no way of knowing what the mixture was. So that means you can't say radiometric dating gives you exact ages. All you can do is say it'll give me a maximum or a minimum, but you really can't use it to determine precise ages. This is a latest version of the periodic table of the elements. We've gone up to element number, I believe it's 120. There are 90 that are known to exist on Earth. So those are the ones we're concerned with. Elements number 43, 61, 93, and above, which are the ones shown in red, are known only in artificially manufactured form. Number 43 is seen in some stars, technetium, which I referred to in the last episode. But according to evolution, the 90 naturally occurring elements, the ones shown in white, must have come from some sort of lighter building blocks. Well, a few episodes earlier, we talked about the possibility of forming any heavier elements from a big bang consisting only of hydrogen, and all you could get would be hydrogen, helium, and perhaps some lithium. That's it. You couldn't get any of these heavier elements because there are some crucial steps that are missing when you're going mass number 1, 2, 3, 4, we get to 5 up, doesn't exist. 6, 7, we get to 8, it doesn't exist. And that would stop you from going any further by purely natural processes. So we don't know how they came about. But according to evolution, the 90 naturally occurring elements shown in white must have come from lighter building blocks. So if we want to have an accurate test, we have a mixture of elements in a rock. Many include a radioactive parent and a radiogenic daughter. So first you have to know the initial percentage of the parent and the daughter in the rock at the beginning. We have no way to know that. And then you have to know that the rate of change has been constant the entire time. We've been watching for somewhere around a century, but we have seen half-lives change under certain circumstances by up to 1 billion times as fast. The radioactive decay rates the published decay rates are averages of experimental values. Some are a little lower, some are a little higher. That's why they're averages. Well, we've been determining the decay rates over less than 100 years, and we're trying to apply them to 4.5 billion years. That's like watching a jet fly past for 1 second and guessing how fast it's been flying for the last 522 days. Why do individual atoms decay? We don't know. Some believe that the decay of individual atoms is purely random. Others believe there's some as yet unknown cause, such as the density of a particle called a neutrino. We don't know for sure. So why did this atom decay and that one didn't? We don't know. We can take a guess. But there have been experiments done that have produced changes in decay rates of at least 14 isotopes of various elements. We can speed things up under the right conditions. Well, under plasma conditions, that is where we remove most or all of the electrons, decay rates have been accelerated up to 1 billion times as fast. Evolutionists believe that the Earth began in plasma conditions, and some creationists also believe that the Earth began in plasma conditions. If that's the case, or the electrons are removed, that would mean that any conclusions you drew about radiometric dating would be unreliable for those elements from the beginning of the Earth. We could have had a great amount and we didn't even know about it. There have been some very interesting recent studies at Purdue and Stanford universities that have showed some anomalies in radioactive decay rates. They seem to depend on the sun. The decay rates go through a 33-day cycle from fastest to slowest. This is believed to be the rotation rate of the sun's core. So when one side points at us, things are faster. When the other side points, things are slower. Also, the decay rates speed up slightly in the winter when we're closer to the sun, and they slow down slightly in the summer when we're farther away. We talked about that earlier, how We're not actually closer to the sun in the summer. Northern hemisphere, we're farther, but the sunlight is more directly on us. So the decay rates vary depending whether we're closer or farther from the sun. And we've also noticed the decay rates slow down slightly just before solar flares. So the sun ejects a large quantity of plasma, gases, and so forth, and the decay rates slow down just before that happens. Why? We don't know. The sun seems to be doing something that affects the decay rates. Perhaps it produces some unknown particle that makes nuclei decay faster. Maybe it's something to do with the neutrinos flowing out from the sun. We don't know. But whatever the cause is, we can say with certainty that radioactive decay rates do change. That means that radiometric dating is unreliable. You have to know all of the circumstances, and you don't. So if we want accurate radiometric dating, first we have to know the initial percentage of parent and daughter. We have no way to know that. Second, we have to know the rate of change. It must have been constant the entire time, or at least we have to know when it's changed and how much. We have no way to know that. We've been watching for less than 100 years, but we have seen half-lives change under certain circumstances by a great many times. And then also, this has to have been a closed system. None of the parent or the daughter can have been added or removed the entire time. Some of these atoms, some of these isotopes of elements are water soluble. So, for instance, uranium decays into lead, while some uranium compounds and some lead compounds are water soluble. Is there any rock on this planet that you can promise me with absolute certainty has never gotten wet? No, of course not. So there's no way to be certain about any of these factors, let alone be certain about all of them. Well, here's another one of the commonly used techniques. It's called potassium-argon dating. This is not used for fossils. This is just used to try to date rocks. So the elements potassium and calcium are abundant in the Earth's rock. Potassium comes in 3 isotopes, and there's one unstable isotope. It makes up just over 1/100th of a percent, has a half-life of about 1.26 billion years. About 89% of the time, that isotope decays into calcium, but the other 11%, it decays into an inert gas called argon. That's used for potassium argon dating because it can be trapped inside a rock. Well, we assume that the rocks formed in a molten state, then solidified after hundreds of millions of years of cooling. Can we be certain of that? Nope. Any argon-40 molten rock would have leaked out. So we use the ratio of potassium-40 to argon-40 to determine how long ago the rock solidified. But here's a problem. If a rock ever heated up enough to soften again, like after a volcanic eruption, then more argon could leak out and give ages that may be wrong by billions of years. When I say they give ages, we calculate the ages. Okay, you've probably heard about carbon dating. In the upper atmosphere, remember, if you didn't know, that the atmosphere is mainly nitrogen. It has a small amount of oxygen and other gases out there, but the most abundant gas by far is nitrogen. So cosmic radiation in the upper atmosphere comes along and it strikes a nitrogen-14 atom, which has 7 protons and 7 neutrons. This turns one of the protons into a neutron. So now we still have the same total number of particles, 14 particles, and it forms an unstable isotope, carbon-14, which has 6 protons and 8 neutrons. The carbon-14 doesn't like itself. It wants to turn into something else, and it's eventually going to decay back from carbon into nitrogen. So meanwhile, the two isotopes of carbon, the 14 and the 12, combine with oxygen in the atmosphere to form carbon dioxide. And then the plants use the carbon 12 from the carbon dioxide and carbon 14. They use that carbon to build up their cell structures. Plants take in carbon dioxide from the atmosphere, and a little political commentary here. We think that, oh, we should trap the carbon dioxide. That's ridiculous. Carbon dioxide is plant food. It's a natural part of the atmosphere. We need to just let it float around and let the plants take hold of it. So, okay, the two different forms of carbon, carbon 14 and carbon 12, they form carbon dioxide, and the plants take that in to build up their cell structures. Then an animal comes along and eats the plants. So the carbon becomes part of that animal now that ate the plant. And then when a plant or animal dies, it stops taking in carbon. The carbon 12 is stable. As long as we can tell, it's just going to remain as carbon 12. But the carbon 14 will decay back to nitrogen 14, and its half-life is about 5,730 years. So we measure the ratio of carbon 14 to carbon 12 in the carcass as compared to the atmosphere, and we can estimate how long ago it died. Here's some problems with carbon dating. Number one, the carbon in many fossils has been replaced by other minerals. Calcium, silicon, things like that. So you can't carbon date something if it doesn't contain carbon. The next problem is if the animal or plant's environment was low in carbon 14, it'll give a false reading much higher than the real age because we're assuming that there was this much carbon 14, maybe not. This happens frequently in sea creatures when they live at the bottom of the lakes and oceans and so forth. The carbon 14 might not have gotten down to the bottom, so they have less than we expect. So they give a false reading that's much higher than the real age. Then the ratio of carbon 14 to carbon 12 in the atmosphere is not constant. It keeps increasing. The older something is, the less carbon 14 was available at the beginning, and the less reliable the carbon date is. So we need to adjust to what we would consider to be old age accordingly, old dates. And carbon 14 has a relatively short half-life. Carbon dating only is used for ages of a few thousand years. It doesn't work for hundreds of thousands and certainly not for millions. So anytime somebody tells you a dinosaur bone was carbon dated at whatever the age, at millions of years, they'll lie about other things too. Carbon dating is only used for ages measured in the thousands of years. So we don't even try to carbon date those. There also can be external factors that'll add or remove carbon or nitrogen. So remember, we have to have a closed system. If it was not closed the whole time, well, we can't be sure. And then some plants seem to be able to exclude carbon 14 from their structures. So that plant, if I pull it out of the ground and do carbon dating on it, is automatically going to show a false age. Or any animals that have had that plant as a major component of their diet, they're also automatically going to show a false age. So we need to be very cautious about claims for carbon dating. Fossils are also not dated by other radiometric methods like potassium argon, because you need a good sized sample of radioactive material to perform the dating tests. In most sediment, the particles are too finely divided for reliable testing. You need a good sized chunk, not just a little grain the size of a grain of sand. So the only kind of radioactive material that can be directly dated is volcanic rock, igneous rock. Yeah, but when that comes out of the volcano, it's so hot that it would have destroyed any living thing in its path rather than preserving it as a fossil. So here's some examples of erroneous radiometric dating dates that we can be sure are wrong. There's a mammoth unearthed in Chekhorovka in Siberia. Its hair was carbon dated at 26,000 years, but the soil was only 5,600 years. Well, how could it sit there for over 20,000 years without being buried or rotting? In Nevada, there have been snails that have been carbon dated at 27,000 years. As I said, if something's underwater, it may not be getting carbon 14 from the atmosphere. Another example, a living clam carbon dated at 2,300 years. Wait, it was alive. And then from the same block of peat in New Zealand, there were two different carbon 14 ages, 15,000 years apart. Dried seal carcasses less than 30 years old were carbon dated as old as 4,600 years. The blood of a freshly killed seal at McMurdo Sound in Antarctica, it was carbon dated at 1,300 years. Rocks containing something called nutcracker man, the potassium argon, dated at 1.75 million years. And then bones found lower were carbon dated. You can't do potassium on bones. You can't do carbon 14 on the rocks. But bones found lower, which should be older, only dated to 10,000 years. Lava rocks from Hualalai in Hawaii were potassium argon dated at almost 3 billion years. The rocks were actually less than 200 years old. We saw them come out of the volcano. Also, other new Hawaiian rocks from the eruption of Kilauea, brand new, they were potassium argon dated at 22 million years. Moon rocks have been dated by various techniques. They've been inconsistent, ranging from 700 million to 28 billion years. And the moon is supposed to be about 4.5 billion years old. At Mount St. Helens up in the state of Washington, lava rocks, we knew the day they came out of the volcano, but they were dated anywhere from 350,000 to 2,800,000 years. But the actual age when they came out of the volcano was 10 years. You say, we must have done something wrong. Absolutely. You can't trust things coming out of volcanoes. There have been some recent carbon dating results I think are very instructive. Recently developed tests for carbon-14 using accelerated mass spectrometry, they're able to detect the presence of carbon-14 at 100,000 times lower concentration than previously. Out of hundreds of supposedly multi-million year samples tested, all but 2 of them contain measurable amounts of carbon-14. Radioactive elements disappear within about 10 half-lives. Even if we're generous and stretch it out to 40 half-lives, within about 250,000 years, all of the carbon-14 should be gone. It's not. Anything you can carbon date has to be less than 250,000 years old, maximum. And it could be anything less. It could only be 10,000 years. In many, many, many cases, they point toward something that happened less than 90,000 years ago. Now, we have got to correct radiometric dating, especially carbon dating, because of decay rates and a lot of things. But this would put a maximum age on all of these fossils of less than 90,000 years. What? You mean they weren't 500 million years, 300 million years? No, less than 90,000 years. So here's one of the latest and greatest techniques, isochron dating. An isochron is an attempt to eliminate the need to know initial parent-to-daughter ratios. Those doing the technique use a radioactive element and 2 different isotopes of the element it decays into. So if you look on the chart there, you'll see that we're going to graph the radioactive parent versus the non-radiogenic isotope. And let's see what we get out of this. We start with the invalid assumption that rocks come out of volcanoes perfectly mixed. We know from observation they don't. but we get a slope on a graph. We arbitrarily assign a meaning to the slope of the line. It could represent millions of years, or billions of years, or thousands of years, or it could be meaningless. We just pick one according to what we want. And there have been some cases where the slope of the line is actually negative, indicating the impossible solution of a negative age. Some time traveler must have come along and put it there. But if any of the non-radiogenic element, the original element, was ever added or removed from any of the samples, this technique is useless. So let me show you what happened. At the Grand Canyon, there's a bunch of volcanic rocks. Basalt is at the bottom of the Grand Canyon. The Cardenas basalt is supposed to be about 1 billion years old. And then up at the top, the Uinkaret Plateau, it's supposed to be about 1 million, which is 1,000 times less old. So somebody decided, let's do some rubidium strontium dating on the top of the on the bottom of the Grand Canyon, the Cardenas basalt. And they had said it's about 1 billion years old. You have to solve an equation. You plug in 5 variables. So they plugged in the appropriate variables to get an age of about 1.07 billion years for the Cardenas basalt. So some of those pesky creationists came along and they said, okay, what were the numbers you used in your equations? We're going to date the top, the Uinkaret Plateau, and find out, does it really come out to be much, much, much younger? No. The same technique with the same numbers was applied to the Uinkaret Plateau. It, rather than showing 1 million years, it showed an age of 1.34 billion years. This is 1,000 times too old. It's 270 million years older than the rocks at the bottom. So we have 2 choices. Number 1, either the technique is faulty or the Grand Canyon's upside down. I'm going to go with the technique is faulty. Well, as you can tell, there's a whole lot more still to go on the topic of the age of the Earth. So I'm trying to keep these to about a half hour each. We'll continue on in the next session talking about more things on the age of the Earth.